Greetings, Honors Chem students. Mr. Keister here with you again today. This is the video for Wednesday, October 7th, 2020, which I believe, yes, is our 34th day of school for the fall semester. Always keep in mind, though, the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at the do-nows and see what our schedule is today. So today is the lab day. So we're going to do lab 2-2 today. Your homework for today was to complete the energy calculations number 2 multi-step processes assignment that we went over yesterday. Turn that in. It is due now. So if you're here in class, that should already be on my desk. If you are at home, you should be submitting that to me when your class period begins, whenever that might be. Send it to me electronically. Of course, you could check your answer before you turn it in. If you're here at school, on the back board, of course. If you're at home, you can check it on the answer keys page in Canvas. Today we're going to complete lab 2-2. It is due today by the end of class. For some reason you don't finish it, which I can't think of a reason why you wouldn't, then I must have it before you leave school today. So if you don't turn it in at the dismissal bell, make sure you swing by here before you leave school today and get it turned in. It is due today. All right. Your next online homework and mastering is due this coming Friday, day after tomorrow, by 7:30 a.m. You should already be working on your Unit 2-2 exam review, which was handed out yesterday. Although it's technically due today by the end of class, I will not collect it until tomorrow, like normal. You may check your answers with the answer key after you show me your paper. Otherwise, it'll be posted in the morning. I'm going to do a separate video for the exam study list and prep, so you can view that one separately. So let's go on to the lab. Let me bring it up here real quick. So there it is. So lab 2-2, density and specific heat capacity of an unknown metal. So I want to look at the first question with you under the pre-lab. You're going to have some time to work on the pre-lab while your metals are heating back there, but I want to at least get started with this part. What type of properties are both density and specific heat capacity, intensive or extensive? Let's think about what those terms mean. Remember, intensive means that property is independent of sample size. It's the same regardless of how large or how small a sample of the substance that you have. Extensive properties do depend on sample size. So think about density. The density of water is 1.00 grams per ml. Does it matter how much water you have? Is that going to affect the density? And the answer is no, it's not. So density is an intensive property. What about specific heat capacity? The specific heat capacity for liquid water is 4.184 joules per gram degree Celsius. Does that heat capacity value change if you have different samples of water? The answer to that question is the same. No, it does not. So both density and specific heat capacity are intensive properties. Intensive. So why then can they be used to identify an unknown metal? Because intensive properties are specific to a particular substance. All right. Each substance has its own density. Each substance has its own specific heat capacity. And so they can be used to help identify an unknown. Okay. That's what we use them for. Question 2, in this lab, you're going to transfer a sample of a hot metal to a cup of room temperature water. All right. So what happens when you do that? Well, the temperature of the metal is going to decrease or go down, and the temperature of the room temp water is going to increase when you put the hot metal into it until they reach some final temperature for both. All right. Then from 2B on down to number 3, it's got some information down here about what we just talked about, transferring a hot metal into room temperature water. You're going to draw an energy bar chart or an LOL chart for the metal, right? Not for the water, for the metal. So label it completely, show how the first law of thermodynamics is followed, draw a completely labeled heating and cooling curve out here in the margin. And then what type of energy flow occurred for the metal when it's placed in the room temp water? Was it endo or exothermic? And the energy absorbed or released by the metal is equal to the energy absorbed or released by the water. All this should be review. We talked about it multiple times. Shouldn't have too much trouble with that. It's good review. And then there's a little sample problem down here regarding energy transfer, just like the ones we have been doing in the past few days. You'll be working on that while you're waiting on your metal to heat. So let's go back there and get started on this thing, and we'll go from there. Okay. There we go. See, I got some water boiling there. All right, so let's go to the back of the front page where the procedure is. So it says record the identification code for your metal. So I'm going to do metal number 1, all right? And so I would record that in my data table, ID number 1. Find the mass of the metal in the tube. Find the volume of the metal in the tube. Clearly record your measurements. Dry the metal and return it to the test tube before we get started. Now, that is not going to be unnecessary. In the interest of time, I have gone ahead and recorded the mass and the volume of each sample for you. It's on a little green card that will be at your lab table. So this is metal number 1, all right? And so its mass is 19.66 grams, and its volume is 7.4 mLs. I did that, of course, by water displacement. I then dried the metal off and returned it to the test tube. So we're ready to move on with the procedure. Place a styrofoam cup into a 250 ml beaker for stability. I've done that. Add approximately 50.0 mLs of water to the cup. All right, so let's see how close to 50 I can get. Of course, the markings here on the cylinder are to the nearest whole number, the ones place, so we're going to record to the first decimal place of the tenths. So I want to get about 50. Let's see how good I am at this. Oh, beautiful. Got the meniscus laying right on the 50, so that would be 50.0 mLs. So let's put that in here. And find the exact mass of the water. Well, the density of water is 1.00 grams per ml. So if I have 50.0 mLs, I would have 50.0 grams. So we'll record that under the mass of the water in the data table. Okay. Now it says, okay, we're going to put the test tube into the hot water bath for 10 minutes. All right. So take the stopper off the test tube. This is number 1. And I'm going to put it in the boiling hot water bath for 10 minutes. Okay, I looked at the time. And while waiting the 10 minutes for your metal to heat, be productive and complete the pre-lab questions. All right? So I'm going to pause this for 10 minutes, and then I will be back, and we will complete the procedure and complete recording the data table. All right? So I'll be back. Hang tight. Work on the pre-lab questions while you are waiting. See you in a bit. Hello, Honors Chem students. I am back again. So it's been about 10 minutes now, and this metal has been in this boiling hot water bath since I last left you. The whole purpose for that was that after that amount of period of time, that the temperature of the metal in the test tube would be the same as the temperature of the boiling water that it has been placed in. So now I'm on procedure number 3. We're going to measure and record the temperature of the room temp water just before adding the metal. So we want to get an initial temperature, or TI, of our room temp water. And let's let it settle in there. And it says 22.0 degrees Celsius. So under room temp water, initial temp 22.0 Celsius. Then it says procedure 4, measure and record the temperature of the hot water bath. This will be the initial temperature for the metal. So I'm assuming it's going to be somewhere around 100, but of course, we're not at standard pressure. Water boils at 100 degrees at standard pressure. We're not quite standard pressure, so it may be a little lower than that. Of course, this may be calibrated not exactly correctly, but we're using the same one for both, so that shouldn't matter. So let's check the temp of the water. Well, that's shooting up there pretty quick. And it says we are at 95.1 degrees Celsius. 95.1. I think the calibration's off a little bit. Well, that's okay. We used the same thermometer for that, so it won't matter. So, next, procedure 5. Using a test tube holder, carefully remove the test tube of metal from the hot water bath and pour the metal into the cup of water. All right, so I'm going to grab that thing and quickly pour all the metal pieces into the room temp water. Cut that off. There we go. Do a quick stir. Okay, so as we talked about in the pre-lab, when you mix these two together, we got an exchange of energy going on. Energy has been released from the hot metal and been absorbed by the room temp water. Same amount of energy, of course, in both. That's the conservation of energy, the first law of thermodynamics. And so we are going to reach a final temperature for both substances. So in our data table down there where it says final temp, it's going to be the same for both the metal and the room temp water. And we have settled in right at 26.5 Celsius. 26.5. Cut that thing off. All right. 26.5 Celsius. So if we, let me fold this up here a little bit. Don't want to give away all the answers. All right, so let's take a look at this data table here, shall we? Get my goggles off so I can see what I'm reading here. All right, so this is the data we have so far. Again, we used metal number 1, so I put the ID number up there. And so as I look at the room temperature water column, our initial mass was 50.0 grams because our initial volume was 50.0 mLs. Again, the density of water is 1. Our initial temp of our room temp water was 22.0 degrees. Our final temp was 26.5 degrees, and I've listed the specific heat capacity for water there, 4.184, which you will need. Then, second column, the metal. Remember this was pre-measured for us, set in the interest of time. So the mass was 19.66 grams. The volume by water displacement was 7.4 mLs. The initial temperature of our metal was the same as the initial temperature of the hot water bath, 95.1 degrees Celsius. And the final temperature of the metal was 26.5, same as it was for the water, because they came to a common final temperature. So there are all the numbers we need to do our calculations. All right. So as I look down at the calculation section, the first one is calculate the density of the metal. Of course, you should be able to do that, I would think. Make sure you round it correctly. Number 2, using your data, calculate the heat energy that the room temperature water absorbed. All right, so this is going to involve, there was a temperature change here, so this is thermal energy change, which means we use the heat equation, Q equal MC delta T. So you have the mass of your water up in the data table, 50.0 grams. We've got the specific heat capacity of water, 4.184. And you need to do your temperature change, which is TF minus TI. Those two numbers, again, for the room temp water are up in the data table. So you would then multiply those numbers out and solve for Q. Of course, it should be a positive answer because the heat energy was absorbed. TF is greater than TI. So we get, this is, of course, an endothermic process. Q is positive. Make sure you round it to the correct number of sig figs. All right. We should go to the next page. Number 3, using your answer from number 2, what amount of energy did the hot metal release? Well, the amount of energy absorbed by the water is the same as the amount of energy released by the metal. So whatever answer you got for number 2, that is the same answer for number 3. And then in number 4, using your data and answer from number 3, calculate the specific heat capacity of the metal. Okay, so here again, we're going to use Q equal MC delta T. Although now Q, of course, we know the value of Q, which we just calculated in number 2. It's the same value in number 3. But now remember that this energy was released by the metal. So when you put Q into your equation here, what are you going to have to do? Since that energy was released, all right? Well, if you said you need to put a negative sign in front of it, you're absolutely right. Yes, you do. All right, so make sure you do that. M, of course, is the mass of the metal, which we had, all right, in the data table. And we're looking for C, and then the temperature change, TF minus TI. Well, remember the metal, the final temperature was 26.5, and the initial was 95.1, which gives us a negative delta T, which it should, all right. We have a negative Q and a negative delta T, so that's going to give us a positive value for C, specific heat capacity, which is what we want. Again, round to the correct number of sig figs. And then based on your density and specific heat capacity, what is the identity of the metal? Okay, so on the, let me see, where is it? Right here. On the pink sheet, which was the instructions for the lab, on the back of that pink sheet is a little data table there that lists the specific heat capacity and the densities for various metals. So based on your density value and your specific heat capacity value, pick which metal comes closest, all right? And you have to do a little figure in there. But again, we're looking for which metal comes the closest overall when given the two values that you have calculated for density and specific heat capacity. And then number 6, it asks you to calculate percent error for your metal sample based on its theoretical value. All right. So the theoretical value for the metal and the theoretical value for the density of that metal for the specific heat capacity and the density are found on, again, on this pink sheet. So those will be your theoretical values. And of course, your actual values are the values you calculated from your lab data. So I think that is it for Lab 2.2. All right. So this is due today by the end of the period. If for some reason you don't have it done, which again, I can't think of why you wouldn't, because I did a lot of the some of the measuring for you early on to help save you some time. If you don't have it turned in by the end of the period, make sure you have it turned in before you leave school today. It is due today. Okay. Again, I'm going to do a separate video on the study list for the exam, which is coming up tomorrow. That video will be posted separately. Make sure you check it out if you are at home. Of course, if you're at school here, you'll hear it from me live today during class before you leave. So anyway, until next time, this is Mr. Keister saying so long. Stay safe, everybody. Take care. Keep focused and keep working hard. See you next time, folks. Take care. So long.